Hello, welcome. This is lecture 5. In this lecture, we're going to recall the definition of the absolute value of a real number. And we will summarize some well-known properties of absolute value. Recall that for every real number x, the absolute value of x is denoted by this symbol and is defined by these formulas. So absolute value of x equals x if the number x is non-negative, or absolute value of x equals negative x if x is itself a negative number. For example, absolute value of 2 equals 2 since x here is positive. And absolute value of negative 3 is negative of negative 3 equals 3. Because x here is negative 3, so we have negative of the x itself, which gives us 3. Now we observe that the absolute value of x is non-negative for all real number x. Since if x is itself non-negative, then absolute value of x by definition equals 2x, which is non-negative. So absolute value of x is non-negative. And if x is itself a negative real number, then by definition absolute value of x equals negative x. But since x is negative, then negative x must be positive, following from the field property. So absolute value of x for a negative real number must be positive, just like this case. So in every case, the absolute value of any real number is a non-negative quantity. The second observation: the absolute value of x equals 0 if and only if x is equal to 0. Because if x is equal to 0, then absolute value of x equals to 0 by definition. Conversely, let absolute value of x equals 0. Now we want to show that x cannot be either positive or it cannot be negative also. So x has to be 0. To show this, let us consider x is a positive quantity. Then absolute value of x equals x by definition of the absolute value. But we have absolute value of x equals 0. So x must be equals to 0, which contradicts our assumption that x was positive. Similarly, if x is negative, then absolute value of x equals negative x by definition. And we must have negative x must be equals to 0 because this quantity is 0. This implies x has to be equal to 0. This also contradicts our assumption that x was negative. So these contradictions prove that absolute value of x equals 0 implies x has to be equal to 0. So no real number other than 0 has the absolute value 0. Theorem. A. The absolute value of negative x equals to the absolute value of x for all real number x. For example, negative 3 has absolute value negative of negative 3 equals 3. But this is exactly same as the absolute value of 3. So both the numbers negative 3 and positive 3 have the same absolute value, namely 3. Statement B. The absolute value of product of two real numbers equals to the product of their absolute values for all real numbers x and y. Statement C. The absolute value of x equals to the non-negative square root of x squared for all real number x. For example, the non-negative square root of 3 squared is 3, or the non-negative square root of negative 4 squared equals non-negative square root of 16 equals positive 4, which is equals to the absolute value of negative 4. Statement D. If R is a positive real number, then the inequality absolute value of x smaller than R would be true if and only if x is greater than negative R and x is smaller than positive R. For example, the inequality is true if and only if x is greater than negative 3 but smaller than positive 3. Statement E. It says for all real number, these inequalities are true. Namely, the negative of the absolute value of x is smaller or equal to x, which is smaller or equal to absolute value of x. For example, the number 2 is larger or equal to the negative of its absolute value. And the number 2 is also smaller or equal to the absolute value of 2. Let's take another example. The number negative 3 is larger or equal to negative of its absolute value, but smaller or equal to its absolute value. Let's try to prove the statement A. The statement A is clearly true for x equals 0, since the absolute value of negative 0 is exactly equal to the absolute value of 0. Now we consider the case where x is a positive real number. If x is positive, then minus x should be a negative real number. Then, by definition, the absolute value of negative x equals to negative of the number itself, namely negative x, which is x itself, following the property of fields. But since x is positive, it must be equal to the absolute value of itself. So we proved that for the case of a positive real number, the absolute value of negative x must be equal to the absolute value of x. Similarly, if x is negative, then minus x must be a positive real number. Please see the notes on fields. Now it follows that the absolute value of negative x is the number itself. since we have negative x is a positive real number. But this is, by definition, the absolute value of x, since x is itself a negative number. This concludes the proof of the statement A. Similarly, please try to prove the other statements. For that, please consult your textbook or see the details in the notes.